We have a function z of two variable which is given by x times f of x plus y times g of x plus y. Using this function, we need to show that the second partial derivative of z with respect to x minus 2 times the second partial derivative of z with respect to y followed by x plus the second partial derivative of z with respect to y equals to 0. So let's begin. So here we have the given function z, which is equals to x times f of x plus y times g multiplied g of x plus y. Let's label this as number 1. We'll take the partial derivative of our function z with respect to x. So that means we'll have to take the partial derivative with respect to x of x times f of x plus y plus partial with respect to x of y times g of x plus y. So let's apply the partial derivative. So here we'll have to use the product rule. So first we'll have partial of x with respect to x. So this will get multiplied to f of x plus y plus x times partial with respect to x of f of x plus y plus again use the product rule to the second partial derivative. So we have partial of y with respect to x times g of x plus y plus y times partial with respect to x of g of x plus y. So partial of x with respect to x, that will be equals to 1. So in the first term we have 1 multiplied to f of x plus y plus x times. Then now we'll have to take the partial derivative of our function f of x plus y with respect to x. So this is the same as taking the partial derivative of f of x plus y with respect to x plus y, which gives us f prime of x plus y. This will get multiplied to partial with respect to x of x plus y as a consequence of applying the chain rule plus partial of y with respect to x. So that will be 0 because y is treated as a constant. So that means this term will go to 0. Now we have the final term. So we have y multiplied to the partial of g of x plus y with respect to x as simply g prime x plus y, where g prime of x plus y is the partial derivative of g of x plus y with respect to x plus y, and then we will multiply it to partial with respect to x of x plus y. So here we have used the chain rule. So that means we now have f of x plus y plus x times f prime of x plus y times now partial of x plus y with respect to x. So that simply equals to partial of x with respect to x, which is 1, plus partial of y with respect to x, which is 0, plus y times g prime of x plus y multiplied to the partial of x with respect to x will be 1, plus partial of y with respect to x will be 0. So this now gives us partial of z with respect to x will be equals to the function f of x plus y plus x times f prime of x plus y plus y times g prime of x plus y. So we're going to label this as equation number 2. In the next step, what we'll do, we'll take the partial derivative on both sides with respect to x again. So we'll have partial of z with respect to x. That means we're taking the second partial of z with respect to x, which will be equals to partial with respect to x of f of x plus y plus partial with respect to x of x times f prime of x plus y plus, so here y is a constant, so we don't have to take its derivative. So this will be simply y multiplied to partial with respect to x of g prime of x plus y. Right. So partial of f of x plus y will be f prime of x plus y. So here f prime of x plus y is the partial derivative of f of x plus y with respect to x plus y and multiply to partial with respect to x of x plus y. So we have used the chain rule here. Here we'll apply the product rule. So we have partial of x with respect to x. So this will get multiplied to f prime of x plus y plus x times partial with respect to x of f prime of x plus y times The partial of g prime of x plus y will be g double prime of x plus y, and this will get multiplied to partial with respect to x of x plus y. Right. So let's simplify it. So we get f prime of x plus y. Now partial of x plus y will be simply 1 plus partial of x with respect to x, so that's 1. So here we have f prime of x plus 1, which would get added to the first time to give us 2 times f prime of x plus y. Coming to the third term, we have x times, so we have to take partial derivative with respect to x of f prime of x plus y, so that will be f double prime of x plus y multiplied to partial with respect to x of x plus y plus y times g double prime of x plus y times partial of x plus y with respect to x will be simply 1. So this gives us 2 times of f prime of x plus y plus x times f double prime of x plus y. This will be 1 plus y times g double prime of x plus y. So let this be number 3, and this is the second partial derivative of z with respect to x. So now again we'll start with the original function z. We'll take the partial derivative of z with respect to y, and I'm writing the result here. So that will be x times f prime of x plus y plus g times of x plus y plus y times g prime of x plus y. So this will let this be number 4. Then we'll take second partial derivative of z with respect to y. That means we'll have to take the partial derivative of number 4, the right hand side of the expression of number 4 with respect to y, and that's going to give us x times f double prime of x plus y plus g prime of x plus y plus, this will become 2g prime. Then we have y times z double prime of x plus y. This will be number 5. We'll use equation number 4, and then we'll first we have partial of z with respect to y. We'll again take its partial derivative with respect to x. So this is going to give us f prime of x plus y plus 2x times plus x times f double prime of x plus y plus g prime of x plus y plus y times g double prime of x plus y. So this will be number 6. Now considering equation 3, 5 and 6, what we'll do, we'll add equation number 3 and equation number 5. That means we have the second partial derivative of our function z with respect to x. Now this will be added to the second partial derivative of the function z with respect to y, and from it we are going to subtract 2 times the partial derivative of function z with respect to y followed by x. So let's do that. So the second partial derivative of z with respect to x will be 2 times f prime of x plus y plus x times f double prime of x plus y plus y times g double prime of x plus y. So this is now added to the second partial derivative of y with respect to z with respect to y, which gives us x times f double prime x plus y plus 2 g prime of x plus y plus y times g double prime of x plus y. So from here we are going to subtract minus 2 times equation number 6. So we have 2 times f prime of x plus y minus 2x f double prime of x plus y minus 2 times g prime of x plus y minus 2y times g double prime of x plus y. Okay, so here we have 2 prime of x plus y, so and this 2 negative 2 prime of x plus y cancelling out. We have x times f double prime of x plus y added to x times f double prime of x plus y, so this will get cancelled out with this term. Then we have this term and this term cancelling out with this term and this one. So that means all the terms cancelled out, and this finally gives us thus the second partial derivative of our function z with respect to x added to the second partial derivative of z with respect to y minus 2 times the second partial derivative of z with respect to y and x. So this will be equals to 0. Hence proved.